students. So in this session we'll discuss about the filter design techniques. So in which we'll discuss about the IIR filter. Last session how to realize the IIR filter with some problems we have discussed. So here what are the different techniques, the transformation techniques. So particularly FR filter and IIR filter techniques we'll discuss. So FIR already we discussed. So for any LTA system, so this is a filter, it may be a filter. So the important class of LTA system, so it's a frequency selective filter. Frequency selective filter. So X of n. So it passes, this filter passes the certain frequency components of the input signal and it will reject the other components. So filter only passes only the certain selected frequency components. So the design of DT filters, filter design, particularly this is DT filters, digital filters. So the design of DT filters corresponding to determine the parameters, of the transfer function, parameters of transfer function, parameters of transfer function. Okay. So which will approximate the desired impulse response or frequency response within the specified tolerances. So the parameters only, okay, of the transfer function that approximates the desired impulse response, or you can say frequency response within the specified tolerances. So normally when digital filters came into the picture, it will be based on the mapping of continuous time filter to analog filter. That means continuous time filter means analog filter to digital filter. Because normally in digital domain, the processing of infinite impulse response is not possible. So that the direct design of IIR filter is not possible. Direct design is not possible. Direct design of IIR filter is not possible in digital domain. In digital domain, the processing of infinite samples of any impulse response is not possible. Therefore, IIR filters are designed via analog filters. So in digital domain, so you know what is transfer function, in which what are the parameters. So in direct digital domain, so the processing of infinite impulse response is not possible. Therefore, IIR filters are designed via analog filters. So what is analog filters? So now analog filters transfer function. So the analog filter transfer function is denoted by H of S. Okay. So the transformation of analog filter, okay, to the transformation of digital filter H of Z is designed to satisfy our condition. So the analog filter is transformed to digital filter with the transfer function. So with respect to poles, we know that the analog transfer function H of S, the Laplace transformation we are using, is stable. When it will be stable, if all poles lie in the left half of the S plane. In the left half of the S plane. Okay, so left half of the S plane, you know that. So for stability, the system function is stable only if the poles are lie on the left half of the S plane. So it's an imaginary axis. So in the imaginary axis, the J omega plus J omega and minus J omega. Okay, so all the poles should lie left half of the S plane. So unlock frequency, you can say this also J omega and plus J omega. This is minus J omega. So this is your S plane. Okay, how the poles are located? So this is your sigma. Okay, so this is a S plane. So all the for stability purpose, all the imaginary axis in the S plane, how it is mapped into Z plane. So this imaginary axis in the S plane is mapped into the unit circle in the Z plane. This is Z plane. So this imaginary axis, this imaginary axis is mapped into unit circle. This is a unit circle in the Z plane. So the left half of the S plane is mapped into interior of the unit circle in the Z plane. So this stable analog filter is converted into stable digital filter. So this is only stable. Left of the poles should lie on the left half of the S plane LHB. This is RHB. Okay, for stability. For stability. So when you map this S plane into Z plane, so the imaginary axis mapped to the unit circle and the left half of the S plane should map into the interior of the unit circle. Okay, there are different analog filters. So the analog filters, different analog filters. The popular one, um, okay, transforming this analog filter, the popular transformation technique, the popular transformation technique, transformation techniques for converting this analog filter to digital filter. The transformation techniques are, there are two techniques, there are different techniques. Okay, direct approximation method and impulse invariance method, bilinear transformation method, match the transform method. There are different IIR filter design. Okay, so in the design of IIR filters, we are specifying the desired filter characteristics for the magnitude response only. So in the IIR filter, we are specifying the filter characteristics for the magnitude response only. For the magnitude response only. In generally, okay, if you want to use any application requires linear phase filter, you can go for the IIR filter. How to choose IIR and the FIR? Depending upon the application, whether you want IIR filter or FIR filter. So FIR filter, you know that there is when there is a requirement of linear phase FIR filter. So here if you see, so FIR and IIR. So compare FIR and IIR. Compare FIR and IIR. It depends upon the our what is the nature of our problem. Okay. In practice, so FIR filters are used only when there is a need of linear phase characteristics. Linear phase characteristics. So because the filter characteristics for the IR filter, it responds only for the magnitude response only. This is only for magnitude response. Magnitude response only. So the same parameters filter same number of parameters. We can use either FIR and IIR. So depending upon the application. And also it has more stability. It is FS, but it is more stable. FS more stable. Okay. So when there is a phase distortion is an unimportant, the phase distortion is an unimportant, then you can choose IIR filter. Preferably you can use IIR filter because this IIR implementation, it involves only fewer parameters. So less memory, it requires less memory and lower complexity. So its implementation, it requires only few parameters, less memory locations and lower complexity. Okay. And also in this, the zeros and poles, normally in the zeros and poles, the number of zeros. So yeah, the transfer function, we use m, the numerator polynomial is m zeros and the denominator polynomial are n poles. So normally the number of zeros should be less than or equal to number of poles. So the filter the log transfer function, you have to satisfy the following the transfer function. So as I said, the unlock filters, the transfer, we'll see what are the different popular unlock filters and what are the different transformation techniques. So as per for the two important transformation techniques are impulse invariant technique, and the second one is the bilinear transformation technique. Bilinear transformation technique. Similarly, the analog filters, the two popular analog filters are the two popular analog filters. One is a Butterworth filter. Second one is the Chebyshev approximation filter. Chebyshev filter. The two analog filters are Butterworth filters. So the transformation techniques used. So what is the need of transformation technique? So for digital filter design, the frequency transformation. Okay, in both analog and digital domain for transforming were low pass prototype. The transformation technique, the frequency transformation. Okay, which is used to transform your low pass prototype into low pass prototype into low pass, high pass, band pass, band stop. The frequency transformation. Frequency transformation from low pass prototype to low pass filter LPF or high pass filter or band pass filter or band stop filter, band elimination or band stop filter. Similarly, one more comparison to analog filter and digital filter. So when you compare analog filter and digital, what are the advantages of digital filter? Because normally in analog filter, the resistors, capacitors, inductors are used. All these will be changed with the temperature. So digital filters don't have these components. They have thermal stability. So in analog filters, because of these components, all these components changes with temperature. So in digital filter, it depends on the precision, the accuracy, more accuracy. Or you can say the precision depends on the length of the registers, length of the registers, memory registers used to store the filter coefficients, the filter coefficients, the filter coefficients. Normally in transfer function is AK and BK are the feed forward and feed backward coefficients, filter coefficients, the AK and BK. So the other advantages of digital filters. So the digital filters are programmable filters. So the filter coefficients you can change at any time. The filter coefficients can be changed at any time to implement the adaptive filters. So adaptive filters, which means adaptive means the filter coefficients AK and BK can be changed at any time. And single filter can be used to process multiple signals. This is a multiplexing techniques can be implemented. Multiplexing techniques. Single filter is used to multiplex to implement that is to process the multiple signals. Generally, the analog transfer function can be described as system function HA of S, which is equal to summation of k equal to 0 to m. That is a here we will use some parameters name S power k by summation of k equal to 0 to n is alpha k S power k S is equal to e power j omega. So we'll write the transfer function. Okay. So the unlock transfer function is the summation of k equal to 0 to n. So this is bk into e power, that is a x power k s power k divided by 1 plus the summation of k equal to 1 to n ak into s power k. So if you substitute s equal to e power minus j omega, okay, so you get e power minus j omega k divided by 1 plus k is equal to 1 to n ak into e power minus j omega k. Okay, this is the frequency response. This is h of omega is equal to j omega. Next, we will discuss about the frequency. Okay, the characteristics of frequency selective filters. So, although the frequency response, the characteristics for ideal filter uh, may be desirable, but in practical applications, we cannot get the ideal one. So, these are the ideal characteristics. Ideal characteristics of this magnitude response h of omega. Okay, it is not possible to realize any filters. We can only approximate the ideal filters as closely as we desire. And also it is not necessary that the magnitude constant magnitude the, should be constant for the entire band. There will be a tolerable ripples in the pass band. There will be a tolerable ripples in the stop band also. So there will be ripples in the stop band. There is a ripples in the pass band. So ripples in the pass band you can specify with respect to del 1. So the tolerable is 1 plus del 1, 1 minus del 1. So ripples in the pass band denoted by del 1 and del 1. Okay. So this is the ideal curve, ideal characteristics. But in practical it will not be ideal. So there will be transition from stop band to pass band to stop band. There will be ripples in the stop band also, that is denoted by del 2. This is del 2. So the passband edge frequency is denoted by omega p and the stop band edge frequency is denoted by omega s. This is omega. So this is pi 0 to pi. So omega p omega s. So this transition from passband to stop band is called transition band. This is passband ripples. This is stop band ripples. So this is the stop band. This is your stop band. Okay, this is your pass band. So this is pass band ripples, pass band ripples. This stop band ripples del 1, pass band ripples, del 2, stop band ripples, and the omega p pass band edge frequency and omega is stop band edge frequency. These are the before proceeding to the filter design, everyone should know the filter characteristics, the magnitude response of the filters, the realizable filters, and what are the specifications of the filter, how to design digital filter. Stop band frequency, pass band edge frequency, and omega is stop band edge frequency. Stop band edge frequency. So the width of the Okay, the width of the omega stop band, or that is omega s minus omega p. The width of the transition band. This is the width of the transition band. Omega s minus omega b. And the width of the pass band. So this is the width of the pass band. This is the width of the pass band. The width of the pass band omega p, okay, is called, so this minus this omega p is called pass band. That is a bandwidth, you can say it's a bandwidth. This width omega p is the bandwidth. So bandwidth is omega p. Okay, so if there is ripples in the pass band filter, then it will be denoted by del 1. If the ripples in the stop band filter, then it is denoted by del 2. And the magnitude response h of omega, which will vary between 1 plus del 1 and 1 minus del 1. So we can say 1 plus or minus del 1 ripples in the pass band. So the ripples in the stop band is del 2. So in order to accommodate the large dynamic range, you can use the logarithmic scale for the magnitude response h of omega. So in the normally in the decibel, the ripples in the pass band will be 20 log 10 del 1 decibels. Similarly, and in stop band 20 log 10 del 2 decibels in the stop band. Okay, the ripples in the pass band you have to represent in terms of decibel. So pass band ripple in decibels, pass band ripples in decibels 20 log 10, 10 del 1, and stop band 20 log 10 del 2 decibels in decibels. In order to accommodate the magnitude response, okay, because it's a large dynamic range, so you can use logarithmic scale. So now, so what is the conclusion? Any filter design problem, you have to specify the maximum tolerable passband ripple. So one is the maximum tolerable ripples in the passband, and the maximum tolerable stop band ripples in the stop band. Then the passband H frequency and the stop band H frequency. The based on these specification, we can select the coefficients, the parameters. It is here. What are the parameters here? The alpha, the bk, and ak coefficients. We can select the bk and ak coefficients. The parameters ak and bk. This is a feed backward coefficient. Feed backward filter coefficients. This is feed forward filter coefficients. Filter coefficients. So we can, according to this specification, we can select the parameters AK and BK in the frequency response characteristics. The frequency response characteristics, there is a h of omega is equal to, this h of omega is equal to the summation of k equal to 0 to m. So bk into e power minus j omega k, when s or k is equal to e power minus j omega divided by 1 plus the summation of k equal to 1 to n ak into e power minus j omega k. So for the given specifications of ripples in the passband, ripples in the stop band, and passband H frequency and the stop band H frequency, we can select the parameters of AK and BK filter coefficients, and Okay, this uh, selection of coefficients approximates the desired specification, and as well as the number of it also depends the number of uh, coefficients is m and n, poles and zeros. Okay, now we'll discuss one of the transformation technique, impulse invariant technique, impulse invariant method or technique. Okay, so how do you the prototype filter, that is prototype filter or analog filter with the transfer function h of s is a transfer function, has an impulse response h of t. So the h of t you can define the inverse Laplace of your h of s. So the in h of s, how many the poles? Okay, m and n, so n poles. In the transfer function, the poles parameters are n poles. So if we consider as n poles, then h of t is equal to the inverse Laplace transformation of h of s, the summation of I equal to 1 to n, the ci, the partial fraction coefficients ci divided by s plus pi poles. So I or k, skr, whatever you can use the parameters, k is equal to 1 also. You can use the parameter k also. Okay, parameter k, you can use parameter k because k is equal to 1 to n s plus pk. So h of t, so ck, this is ck. So h of t, so now you can write h of t is equal to, so what is the Laplace transformation of e power minus alpha into t is equal to 1 by s plus alpha. Okay, so now take inverse Laplace of 1 by s plus alpha. You can write the summation of k equal to 1 to n ck into e power, okay, e power minus, this is alpha, so this is pk, e power minus pk t, e power minus alpha t is equal to 1 by s plus alpha. So for the impulse invariant method, okay, the digital filters required at the sampling instance to have impulse response values. So now in digital filters, okay, we are going to sampling at a distinct values. So you can replace t by n2 sampling. So you will get, that means h of n is equal to h of t for t equal to sampling at distinct intervals. Sampling instance, sampling at a distinct points. Okay, where t is the sampling period. So h of n is equal to, now you can write h of n is equal to the summation of k equal to 1 to n, 1 to n ck into e power minus pk into t is replaced by n2. And now you take the transfer function, digital transfer function h of z. Okay, So the summation of k equal to 1 to n, the partial fraction, the coefficients. So the ck, so here the ck is partial fraction coefficients. The coefficients in the partial fraction expansion. Partial fraction. Okay, so you can write the ck into, so you can apply 1 by s plus alpha 1 by, okay, what is h of z? Actually z transform of h of n. Okay, h of z is equal to the summation of h of n into the problem minus n. Okay, h of n is equal to n is equal to 0 to infinity. So what is so now you can substitute the summation of n equal to 0 to infinity. So n equals 0 to infinity. I hope you understood. So take h of z. So the summation of k equal to 1 to n ck into e power this h of n e power minus pk into n to, that is a sampling period, into z power minus n to z power minus n. So we can write the summation of k equal to 1 to n ck, take it outside, and the summation of n equal to 0 to infinity. So there is a e power minus pk into, that is pk n is 2 is 1, pk into z power minus 1 power n you can write. Okay, this is t is 1, actually t. So this inner term converges into 1 divided by 1 minus e power minus pkt into z minus 1. So this term converges into, this term converges to, you know that 1 by 1 minus e power minus pkt z minus 1. So by s plus pk transformed into 1 by 1 minus e power minus pk t into z minus 1 is transformed. So now you can write it is 1 by, what is it, h of z. So h of z can be written as the summation of k equal to 1 to n. So that is a ck into 1 divided by 1 minus e power minus pkt is a sampling period z n. So this is the impulse invariant technique. So for a given prototype analog filter, so we can transform, okay, into the digital filter h of z by using impulse invariant method, summation of k equal to 1 to n ck into 1 by 1 minus e power minus pk t into z minus 1. So this is a transformation. This is only transformation. Impulse invariant transformation means S to Z by using impulse invariant method. Impulse invariant technique. There are two techniques to transform this S domain to Z domain. So one is the impulse invariant method, so which is h of z is equal to summation of k equal to 1 to n ck 1 divided by 1 minus e power minus pkt. That is very important. For this, we'll take one or two problems. We'll solve one or two problems in this session. Okay, and also the pole. So S is equal to the analog pole. The analog pole S is equal to pk is transferred to a digital pole at z equal to e power pk2 so mapping of points from the s plane to the z plane. So z equal to e power st. So what is S is equal to? You know that S is equal to sigma plus j omega. Okay, Z in polar transform. In polar form, you can represent Z is equal to R into e power j omega. So now you substitute R into this S is equal to sigma plus j omega. So what is sigma? So R into Z here. Z equal to e power st. Okay. So now Z is equal to Z. What is Z is equal to this? Z equal to R power. Substitute here. Substitute Z equal to R power e omega into this equation. R into e power j omega is equal to e power what is S sigma plus j omega to t. So what is a real term R? So you can expand this one e power sigma t plus e power j omega t. So omega t capital T I put sampling period. So R is equal to real term R is equal to, so this is a real term R. So R is equal to e power sigma t. But what is omega? Omega is equal to, so this is omega. Omega is equal to omega t. So omega is equal to omega t, or you can say omega is equal to omega by t. So this is important. So the relationship between analog and digital frequency. So this is a relationship between analog and digital frequency. Okay. So with this we can conclude the session. The next session will discuss about some of the problems by using impulse invariant method.